So using our t result for integration, we let t equal tan x on 2, so it's like the half angle. And we're more interested in just the sine and cosine for this. So sine of x is 2t on 1 plus t squared, cos x is 1 minus t squared on 1 plus t squared, we know that. Now if I want to do the substitution, because essentially it's going to be a substitution, we're going to substitute t equals tan x on 2. I need to work out then dt, or dx, it doesn't really matter. But dt dx, if I differentiate the tan x on 2, I get a half sec squared x on 2. Playing around with that, sec squared is 1 plus tan squared, which I can now say is 1 plus t squared. I'll make dx the subject, because essentially what we've now just created is just another t result. You do not have to go and derive that every single time. The same as you don't derive the t result for sine x each time, and you don't derive the t result for cos x. This is just now another t result. If I'm doing the substitution t equals tan x on 2, dx is 2 to t on 1 plus t squared. And it's useful for integrals like this, because there's no way, looking at it, I can create derivative and function there, because the derivative of cos x is sine x. How on earth would I get sine x into this trig integral? So I'll let t equal tan x on 2. Therefore dx is 2 to t on 1 plus t squared. Now why this is nice for sines and coses, because the denominator in all three of those t results, the sine x, the cos x and the dx, all have a denominator of 1 plus t squared. So it makes the maths really nice, because when I substitute in, I can get rid of the denominator by multiplying by 1 plus t squared. And I end up with a quadratic denominator question in this case. And this one's a nice one because it's just our inverse tan function. So I get 2 on root 13 inverse tan of t on root 13, but now I substitute back and I get this expression. Now be very careful. It's so tempting to move that 2 to the bottom of the fraction and go 2 root 13, but remember, that's part of the angle. You can't just take that out of the tan itself. So 2 on root 13, inverse tan x on 2 on root 13. Last year's HSC had this one, had to evaluate that. So again, I look at it and I go, well, it's a trig, but I can't get cos theta in there anywhere. So I'm going to do this with a t result. So I'll let t equal tan theta on 2, so the theta is 2 to t on 1 plus t squared. Let's work out our limits. Now, as I say, the reality is when I substitute in, I don't actually write the denominator in, because I know it's going to cancel. So therefore, the top just becomes 2 to t. The bottom becomes 2t, but what I've got to be careful with in the denominator, if there is a constant, that will need to be multiplied by 1 plus t squared. Because effectively, I'm just not writing that middle line down of the 2 to t on 1 plus t squared over the, what would it be, 2t on 1 plus t squared plus 1. And I'm multiplying everything by 1 plus t squared. So that bottom of the fraction now becomes a perfect square. So that's nice. We just can add 1 to the power over the power, so we get 1 on 1 plus t, or negative. Substituting in, we get our result. You don't have to only use these for when it's sine x and cos x. If it was sine 2x and cos 2x, I can still use the t result, because remember, all the t results are half angle results. So if it was sine 2x or cos 2x, I'll make t equal tan x. But that's where we've got to be careful. Let's see what happens to our dx when we do that. Differentiate the tan, we get sec squared. That's 1 plus tan squared, which is 1 plus t squared. So now dx will be dt on 1 plus t squared, not 2 to t on 1 plus t squared. In general, if you want to substitute in tan x on a, you can do it. There's the proof, but essentially we just end up with a dt on 1 plus t squared. Now, by far the most common one we're going to do is tan x on 2. Maybe the tan x, and I don't know that, to be honest, I've ever used it for anything other than those two. But we could, so the a's match up. So that's using t results as a trig substitution.